Here's the key for Exam 1, Spring 2018. We're asked to provide the IUPAC name for this compound. This is obviously an epoxide, so we can name it as a substituted oxirane, in which case we would number the oxygen as number 1 and the 2 carbons in the 3-membered ring 2 and 3. And we would choose them so that they would go in numerical order when we list the substituents. So this would be 2-methyl, 3-propyl, oxirane. And then if we're going to assign stereochemistry, there are 2 stereocenters here. So if I look at this carbon, the highest priority is the oxygen, and then the other carbon bearing the oxygen, and then the methyl. And if I count 1, 2, 3, that is counterclockwise, but the hydrogen is towards me, so this is R. So that's 2R. And let's switch colors, look at the other carbon. We'll look at this carbon. Again, the oxygen is highest priority, then the other carbon in the ring, because it bears an oxygen, and then the longer, or the substituent, is 3. The hydrogen is lowest priority. The numbers go 1, 2, 3 in a clockwise direction, so we have also 3R. So finishing up my name, 2R, 3R. That would be one way to name this. We could also name it as a substituent on the long parent chain. So I'm going to erase these numbers here, and we'll come up with some new ones. So the parent chain is 6 carbons long. I'm going to start numbering the parent chain nearest the epoxide. So I have hexane as my parent chain, and I have 2,3-epoxy hexane. And we use the same stereochemistry as we had in the previous one. And just by dumb luck, it's still 2R, 3R. So either of these names would work. I accepted either of them. Here's a roadmap problem where you're asked to fill in some reagents and or other compounds. The first one is a Grignard that is reacting to form a secondary alcohol. So we're going to make this bond right here. This is our original Grignard. I need to draw something that looks like this, but that would react with a Grignard, and that is an aldehyde. We know that Grignards plus aldehydes make secondary alcohols. So some students didn't have the double bond here. They had an O- or something, but I hope you recognize that you needed to have the aldehyde. The Grignard attacks the aldehyde, pushes electrons onto the O, giving us an O-. Then we eliminate the OH using strong acid and heat to get the alkene. If the alkene goes away, this is a reaction from last semester, palladium or platinum or nickel, and hydrogen. Then we got a preview of the aromatic substitution chapter. We can put a bromine on an aromatic ring using FeBr3 and Br2. And then we have a bromine here. We've got magnesium. Hopefully you remember that from lab. That is forming the Grignard reagent. And the Grignard reagent reacts with epoxides to ring open them. This is a simple epoxide, ethylene oxide. And it would give us a, so let's just look at this a little more carefully. Remember that the epoxide ring opening by a Grignard goes like that. A lot of students drew something that looked like this. They wanted to have the epoxide as a substituent there. I'm not really sure where that was going, but we should have ring opened the epoxide. And then we protonate and we end up with a primary alcohol. And lastly, the primary alcohol can be oxidized to the carboxylic acid with H2CrO4 and water. You could have used Na2Cr2O7 and acid and water if you wished, but we needed to oxidize that fully to the carboxylic acid. All right, I hope that question 3 looked familiar to you. This is what we did in lab. So if you had trouble with this, you should refer back to your Grignard lab report. We have excess phenyl Grignard. We're going to add that to the ester, just like we always do. A lot of students wanted to draw these red arrows and immediately losing the methoxide, and that was not the correct way to go. We were going to push electrons onto the carbonyl oxygen and Then we can drop the electrons back to the pi bond, losing the methoxide, reforming the carbonyl, and that's going to react even more quickly with another equivalent of Grignard. We gave you a big clue right here where it said excess. So excess Grignard. Here's our second Grignard. We're going to have that react with our newly formed carbonyl species. Then we all had fun drawing large phenyl rings. And finally, I can take this back to the product. I'm going to abbreviate now. The second step, H30 plus. I would prefer that you draw H30 plus like that. I know I abbreviate it sometimes, but I would like to know that you can draw both of those arrows like that. So this is straight out of lab. It was no different than lab. So if you had trouble with that, you should certainly take a look at your Grignard addition to esters back in the alcohol chapter, but also refresh your memory about the Grignard lab. On to page 2. We had 3 spectra that we wanted you to analyze. The first spectra was kind of boring. You should recognize that this is a proton NMR spectrum because we go from 0 to 10. There is one signal here. This is a singlet. So we have just one type of hydrogen. It does not have any neighbors that are different from it. That's what the singlet is telling us. And so if we looked at any of the hydrogens on hexane here, this would be expected to be a triplet. It's got 2 neighbors that are different from it. This CH2 group would be expected to be probably a sextet. It has 5 neighbors that are different from it. And this CH2 would be expected to be a pentet. It has 4 neighbors that are different from it. So hexane does not make this spectrum. Here we have a little more symmetry here. A lot of students did circle this molecule, claiming that it had high symmetry, only one type of hydrogen. Remember though, while these 4 methyls are the same, there's still CH2s or CHs right here that are not the same. So this would have 2 signals. 2 signals. This would have 3. And this ring, some students confuse this with an aromatic ring. It is not aromatic. There are not pi bonds in this ring. This is cyclohexane. It has 6 equivalent CH2s by symmetry. So you would circle that. And if you wanted to just tell me that this hexane would have 3 signals and this slightly more symmetrical molecule would have 2 signals, that's really all I needed for that one. Moving on to part B. Obviously, this peak is very diagnostic. It's a carbonyl that allows us to rule out none of these, actually, so that's not that useful in this case. But then hopefully you remember from the book, from our discussion in class, that we have this large hump that is shifted. If it were an alcohol, we would expect a hump kind of like that. But you'll notice that the blue one is shifted. And if you refer to the table of data on the back of this exam, you'll see that carboxylic acid OH groups typically span 3,000. They go to almost 2,500 to 3,500. So they span a lot. They're kind of interfering with what we come to expect as the CH3 type hydrogens. So that's the diagnostic peak that helps us decide between this OH containing functional group and the standard alcohol OH containing functional group. So we should circle that one. And the diagnostic is basically this range is for carboxylic acid OH groups. And if you wanted to list that range for me, that would be great. I can't look it up exactly right now. Again, my video recording program doesn't really allow me to go back and forth very easily, but you can look that up in the table. It was the table at the end of the exam. I believe it's 15.2. Here we have a number of esters that we had to analyze and decipher. There were no integrations here. Again, this is a proton NMR spectrum from 0 to 11 ppm. There were no integrations, but we can see that there are certainly 3 signals. And this allows us to rule out that compound. There are 4 signals here. These 2 CH2s are different. One is next to an O, one is only next to a carbonyl. Thus, the methyls attached to those CH2s would be slightly different as well. So we would expect 4 different signals. In addition, each of the hydrogens here has nearest neighbors that would cause it to split. This is a singlet. This whatever hydrogens these are, have nearest neighbors, have no nearest neighbors, so they have no splitting. So that is probably either this methyl or this methyl. And now that we're on that, hopefully you can look at and understand that these two methyls should have significantly different shifts. One of them is connected to an O that's connected to a carbonyl. One of them is directly attached to a carbonyl. And so the shift of this one should be 3.9 or so. And the shift of this one should be about 2.2. And so you'll see that the signal here, the singlet at 2.1, 2.2, is much more indicative of this methyl than it is over here. Alternatively, we could look at these CH2s. These CH2s would both be quartets, and they would have different shifts based on their environment. This one is next to an O. We would expect it to shift to about 4, 4.2. That's what we see here. This one is next to a carbonyl. We would expect it to shift to 2, 2.2 or so. We do not see a quartet right here, so that rules out that molecule. So ethyl acetate is the answer. And basically I wanted you to say something about how 4 signals rules out the middle one, and how one of these peaks, either one, doesn't matter, or both, helps you rule out the rightmost molecule. Here are better choice questions. The first one, we have what looks like Grignard addition to a carbonyl followed by acid workup, or we have TMS chloride that is protecting the alcohol, then Grignard addition, then acid workup, then removal of the alcohol, both to get to the same product. So which of these is the better choice? Well, most of you remembered that Grignards will react with alcohols much faster than they will react with carbonyl species. So the top reaction would probably result in this ethyl Grignard being protonated to form ethane and not reacting with the carbonyl. So it's much better to protect the OH, then do the Grignard addition, then deprotect everything. So we can say up here, alcohol requires protection before Grignard addition. Letter B. Here we have some epoxides. We're going to pop them open with sodium cyanide. So we've got a good nucleophile here. Follow that up with mild acid workup. Same procedure for both, so must be that the differences are here. And indeed, the cyanide is added to the less hindered side on top, or the more hindered side on the bottom. So we need to figure out which of these would be the better option. This is a strong base / strong nucleophile. Better nucleophile than a base, but we're not doing these under acidic conditions. So we would expect the strong nucleophile to attack at this carbon here, thereby putting the cyanide right here as it is on the top. So we would circle the top and just say these conditions are strong base, or I'm sorry, strong nucleophile would result in less substituted side receiving the nucleophile. I think I have an extra E there, but don't hold that against me. All right, C has a aldehyde and ester molecule, and we either treat them with lithium aluminum hydride followed by acid workup, or sodium borohydride in methanol to get this diol. And the difference here then, of course, is these reducing agents. Sodium borohydride will not reduce esters, so it will not produce this primary alcohol on the right side. So we should not use sodium borohydride if this is our desired product. So the top should be circled, and you could write NaBH4, not strong enough to reduce esters. And maybe just more, LAH would reduce both. All right, number 6. Number 6 is an epoxide. It has two different substitutions. It has a tertiary side and a secondary side. We are in acid, and we have a weak nucleophile / weak base, propanol. I have to say I was rather disappointed in the performance on this question. There's a mechanism straight out of the book. I think Skill Builder 14.5 shows the acid catalyzed ring opening of epoxides. had a lot of weird things going on here. So let's look at the proper mechanism first. One thing about this is a fun with acid problem. Whenever you are how do we know that? We've got strong acid here. That's the only clue we need to know that we have a fun with acid problem. That means you should be drawing cations all over the place. You should not use this sulfuric acid as a nucleophile. You should not use it as a base. You should not use it as anything except a strong acid. It provides hydrogens. And that means that you should not remove this H in the presence of strong acid. You'll make a really strong base if you remove this proton. It is not acidic. Do not remove that proton. The protons you need come from strong acid. So anytime you have anytime you have a fun with acid problem, the first step should be protonation. There's really nothing to think about there. You say, hey, I have a strong acid, let's protonate. So now we've protonated our epoxide. We have a better electrophile. We can take our weak nucleophile. This is a weak nucleophile. It reacts better with a protonated epoxide than it does with a neutral epoxide. So now we can take the weak nucleophile, we can use it to ring open on the more substituted side. This is an SN2 style attack as well. So don't forget to take into account the inversion of the stereochemistry. I had a lot of students who neglected to show me that inversion. Also, I'd like to point out that this O makes a new bond to this carbon. This H is along for the ride. Don't lose it. It's not going anywhere. It is not affected by your arrow push. So if you've drawn this arrow properly, and this arrow here, you should have an O with 3 bonds to it, including this H. And that means you have one final step before we have our product. This is a proton transfer step, and we could use a couple of bases. We could use propanol. We could use the starting material. I'm not going to draw it very well here, just so I get it there. We could use HSO4 if we wanted to. I would prefer either the starting material or the alcohol. Most likely one of those is the culprit here. So let's use the alcohol as our base. That's going to do our final proton transfer step, giving us a neutral molecule. Let me erase these words here so they don't get confusing here. So a few important points. We've inverted the stereochemistry at this stereocenter. See, the methyl is a wedge here. It's now a dash. I'm sorry. It's a dash here. It's now a wedge. And so the inversion has happened. Students lost points because they weren't paying attention for that. Also, students didn't recognize this as an acid-catalyzed ring opening, so they added their nucleophile at the less hindered side. That's a good way to lose some points. There's some acid here. Everyone should know what sulfuric acid does at this point. All it does is provide provide hydrogens. Let's look at a couple of options that some students presented that I didn't particularly care for, and I want to hopefully prevent you from doing that same thing. So some students started their arrow between the carbon and the O, and they drew an arrow like that without any second arrow, and their product looked like this. So, for one, don't start an arrow at a bond, especially a single bond. Maybe a pi bond, maybe the pi bond of a double bond, but don't start at a single bond. Also, how do we make this CC bond that was indicated in the product? We didn't do anything with this methyl, so I don't know how this CC bond appeared. That was another problem. Another issue was that students did start their arrow at that CC bond, and they use this green arrow here. That's totally wrong. Do not start the arrow at a methyl. There's no lone pairs. There's no pi bond. Methyls are not nucleophiles. A third option, students took the epoxide and removed the H so that they could protonate the epoxide. Somehow, they would prefer to use this very weak base to attack this very weak acid to produce this very strong acid and this very strong base, instead of just using this really strong acid that we already had to protonate the epoxide. This is correct. This is what we want, but don't use this hydrogen. And this will never form in strong acid. So students who drew this black arrow and the resulting black products got very few points on this basically because they showed that they didn't remember a darn thing about Chapter 3, the acid-base reaction chapter. So I encourage you to look at what you did here for number 6. The blue is correct. These are some common errors that we saw. Really, it came down to students. It appeared that some students forgot how to draw SN2 type mechanistic arrows, which have typically 1 or 2 arrows. In this case, we had 2. The first was nucleophilic attack, and then we lost a leaving group here that remained attached to the molecule. So you may need to review that before we get too far along this semester. Question 7 basically just asked for predict the products. I didn't have too many issues with this. Most students had no problem. So this is asymmetric epoxidation. This is a minus DET. And so when we draw our alkene in the position that Dr. Sharpless recommended, we can observe that we would add the epoxide to the bottom of this alkene, and so we could just leave it in this position and draw a couple of dashes, and that's really all we wanted to do. If you put wedges there, you lost half credit, because the whole point of asymmetric epoxidation is to make only one enantiomer. All right, next we're taking the phenol and we're turning it into an ether. All we have to do is remove this H and give it a good SN2 substrate. So the first step typically is to remove the H with sodium hydride, and then just choose your favorite 3-carbon alkylating agent. Chlorine, bromine, iodine, they all work just fine. Tosylate works fine too. Part C, the first step came from the triple bond chapter, and that was how to make a ketone out of a alkyne. And then we added Grignard and worked up with acid, so the final product should be that species right there. For D, the changes are taking the carbonyl to an alcohol. So all we have to do is reduce this. We don't need to use lithium aluminum hydride. We can use sodium borohydride and methanol mixed together. Those are proper reducing conditions for this molecule. Some students did get confused. They tried to use oxidizing conditions like chromic acid or swern. Here they just mixed up the fact that we needed to reduce this ketone to make an alcohol. For part E, we've got a sulfur anion as a nucleophile. We've got propyl bromide as an electrophile. This is actually a simple SN2 process. I could have asked you this last semester, but this is a thioether, and it fits right into our chapter on ethers, epoxides, and thiols. So this is a thioether synthesis. For F, we've got this mixture of products. Some students confuse this with TMS chloride. I can sort of understand why you might have done that, but this is the Swern oxidation conditions. It was mentioned in the notes in the problem set. So really all you had to do here was basically treat it as like it was PCC. It does the same thing. We're just going to oxidize that alcohol to a ketone. For G, we're taking this chiral alcohol and inverting it to make a chiral bromide. There are several options here. The one I was looking for was PBr3. That's what we learned in the alcohol chapter. But one could also have used tosyl chloride pyridine and just sodium bromide as your nucleophile. So these conditions would have been proper back in chapter 7 when we learned about SN2 type reactions. But PBr3 is what we learned this semester. Either of these is perfectly fine. If you used HBr, you got half credit. The problem is HBr would be SN1 conditions. That would not ensure that we get just this enantiomer. Also, HBr would react with this alkene, as we learned in the addition to alkene chapter. Lastly, PCC plus a primary alcohol. That's why we have PCC. We make the aldehyde. Some students drew this product. That's just a single bond right there. And they added a carbon somehow, so I gave them half credit for that. But hopefully you recognize that there's only one carbon right here. That's that same carbon. There's that carbon. Now I have carbon number 2. So if you drew the green structure, you got half credit. All right, here's another NMR structure problem, and the first step that most students did was to establish the HDI. 5 times 2 plus 2 minus 10, all divided by 2, and that is 10 plus 2 is 12, minus 10 is 2, 2 over 2 is 1. So we have one hydrogen deficiency index here. That probably is accounted for in the C13 data. 208 is a pretty good indication that we have a carbonyl, and we have 5 different carbons, and I have 4 hydrogen signals. And we can analyze the most interesting signal is probably this 3 hydrogen singlet here, because what that tells me is that I have a carbon with 3 hydrogens on it that is not next to any other hydrogens. Plus it's shifted to, let's see, 2.2. So a methyl shifted to 2.2 in a singlet is very likely going to be a methyl next to a carbonyl. And of course, if you're following along at home, that only leaves me with 3 more carbons out of my chemical formula. And I have 3 sets of hydrogens that are probably part of those carbons. So most likely I've got a CH2, and a CH3. There's really only one way to put those together once I've established that I have a methyl ketone, and that is this structure. Some students suggested this structure, and I argued that these carbons are the same, or these hydrogens are the same, and these hydrogens are the same by symmetry. So I'd only expect 2 signals in the proton NMR spectrum, and these carbons are the same by symmetry, and these carbons are the same by symmetry. So I'd only expect 3 carbons in the C13 NMR data. Other students proposed aldehyde of some varying substitution. This has 4 types of hydrogens here, plus the aldehydes. So I think we'd see an aldehyde peak way over at 9 to 10 ppm. We don't see that. You can assume I didn't cut off any important information when I showed you the proton NMR spectrum. So that's one argument against that. And I also would not have a 3 hydrogen singlet here, along with a 3 hydrogen triplet. There's only one place I would have 3 hydrogens on this green molecule. This one would be a 3 hydrogen triplet, but I wouldn't have this signal at all. So I can rule out the green molecule. I can draw another quick green molecule. Some students wanted, let's see, that or other substitution patterns. Basically the same argument. There is no H that's part of an aldehyde here. Okay, let's look at the synthesis. The first one is a tertiary alcohol, where we've added probably this aromatic ring. We've added to this carbon. And so in order to make that CC bond, we probably need a Grignard worked up with mild acid and a carbonyl in that position, and we'll end up with a tertiary alcohol. So the question then becomes, how do I put a carbonyl on this blue dot here on my starting material? Well, remember, if you have an alcohol in that position, you can convert that to a carbonyl very easily. And so I think probably the best way to do this is to put the alcohol on there. And remember that an alkene, we can always add an alcohol to, based on what we learned in first semester, and that's just my favorite reaction, BH3, THF, NaOH, H2O2, so hydroboration oxidation. If you do not know this, you should know this. You'll probably see this on every subsequent exam. It's just because it's so useful. It's very easy to put an OH on this position. In fact, a lot of students tried that. They used, some just added acid and said, oh, I made the OH appear where I wanted it to. Well, that's not going to work, right? Acid is going to put the OH here, not here. Some students added HGOAC with water and said, great, I'm going to get the OH where I want it. No, that's going to add the OH right here as well. The only way to put a functional group here is with hydroboration oxidation or HBr and peroxides. You could put a Br here and eventually turn that into a ketone. That would be a few more steps than I showed you with my 3-step sequence, but you could do it. There's only 2 ways to put a functional group on this position. So you should know those two ways because they're very useful. Let's look at the second synthesis. It appears that we're just taking this methyl and adding an ethoxide to it, but we really haven't learned any way of turning a methyl into a good electrophile or way to receive a nucleophile. The fact that we have two functional groups here indicates that maybe we made that three-membered ring, the epoxide, in order to get those two functional groups. And certainly an alcohol can be easily converted to a chloride, just like a chloride could be converted to an alcohol or an alkene. And so if you're not familiar with these manipulations, you need to review the summary pages of several chapters in your textbook. So most likely, I think, we are converting a ring-opened epoxide into the chloride. We can do that with SOCl2. That's something we learned from this alcohol chapter a few weeks ago. That's probably the easiest way to do this. You could also tosylate it and add NaCl as a nucleophile. This is the result of ring opening under basic conditions and then adding mild acid to work up. We know that we want, if I have an epoxide on these two carbons, I want to open that epoxide on the least substituted position. That's going to be strong nucleophile conditions, not acid conditions. So I'm going to use my ethoxide as my strong nucleophile, and there's my epoxide. So epoxide plus strong nucleophile will give me this setup after I work it up. And then I need to get to the epoxide from the chloride. Very easy to make epoxides from anything that has an alkene in it. And it's very easy to get to that alkene using a strong base. We would also want to use a large bulky base so that we prefer to remove this hydrogen rather than the hydrogen at the interior side. So we'd use a large bulky base to produce the exterior alkene, the less substituted alkene, and then we can convert that to the epoxide with MCPBA. We can ring open the epoxide on this position right here, giving us this molecule. I can convert the OH back to a chloride with SOCl2. Finally, we're using the bonus question. This is another fun with acid. Hopefully you recognize that. Whenever you're faced with a fun with acid, remember, protonate. That's all you need to do, protonate. So let's protonate one of these OHs using our strong acid. Let's see where that gets us. Well, whenever we protonate an alcohol, we have a good leaving group. And if that's a tertiary alcohol, maybe we should just lose it. And if we observe the indicated product, one of these methyls has clearly migrated over to the other methyl. I think we're in a position to do that now. I have a tertiary carbocation. I have a methyl that can migrate next to it. So let's go ahead and do the methyl shift. Here's where some students decided that they were just going to take some random base, not a very good base, but remove that not quite acidic hydrogen to make this molecule. There's really no reason to do that. Certainly we don't need to do that because we already have a very high energy species. Just let it react on its own. Also, we're not going to make these separated charges. That's not very likely. So the green arrows are very unlikely. Let me erase a couple of them. And another clue is that I asked you to show resonance. And here we have a cation next to a lone pair. Indeed, that is resonance. And if you draw the resonance structure, you'll see that we're pretty much at the product. We just need to remove that extra hydrogen. Now this hydrogen is very acidic. We can take water or anything else that we want, remove that H, proton transfer, to produce the desired product. So it's much better to remove this H once I've formed a a three-bonded oxygen with a cation than it is to remove the H right here. And so it's also better to show the resonance that we have a very stable cation now. This cation is more stable than this cation because this cation has no resonance. So that's how I would draw the mechanism for this pinnacle rearrangement.